Now let's solve this question to understand completely what's the idea of the Lenz law. Now here in this situation, we are given with some planar loops and they are of different shapes that are moving out or into a region of a magnetic field. So this cross is representing the magnetic field that is perpendicular to the plane of the screen pointing away from you. Now these are the loops. This is loop 1, this is loop 2, this is loop 3. What you have to determine the direction of induced current in each loop using Lenz law. Now let me remind you that what Lenz law is. So basically Lenz law says that whenever there is a change in magnetic flux associated with a closed loop, an induced current will set up in the circuit. The direction of induced current will be such that it will oppose the change that is producing it. Now see, for the first option, let's see. Now when you are pulling this loop inside this magnetic field, so what you can say, the flux that is here will increase. Now flux is growing, flux will grow. For the first case, when you pull inside, when you pull this loop inside, the flux will increase, right? Now when the flux will increase, means the flux is changing. So the Lenz law says that the direction of induced current, the current that will set up in the coil, the direction of that current is such that it will not let the loop to come inside, means, or it will oppose the factor that is producing it. So what is producing the current here? The flux, the change in flux is creating the current here. So what the current will do, it will not let the flux to increase. Now how it will not let the flux to increase? So it will create a magnetic field perpendicular to the screen towards you, because already established field is away from you. So it will create a magnetic field in the direction opposite to already existing magnetic field. So the direction of induced current will be such that use your right hand. Now curl your fingers in the direction of the induced current. So when you curl your fingers of the right hand in the direction of the induced current, so the thumb, now in this situation the thumb is pointing towards you. So when the thumb is pointing towards you, means this is the direction of the induced magnetic field. Now that field is opposite to the field that is already existing. So this new induced field will reduce the already existing field. Hence, the net flux through the loop will decrease. So in this situation, the direction of induced current will be A, B, C, D, A. A, B, C, D, A. So the current will follow this path. Now for the second case, now see, we are pulling it outside. Now when we are pulling this loop outside, this means what? The flux is decreasing. Now when the flux is decreasing, okay, now the current will set up in such a way that it will not let the flux to decrease, means it will support the already existing magnetic field. So the direction of the current will be in this sense, means in the clockwise sense. So when you curl the fingers of your right hand in the direction of the flow of the current, now the thumb will point in the already existing direction of the magnetic field, means away from you, and this new induced field is supporting the already existing field. So this means it is trying to increase the magnetic field, right? So in this question the answer will be A, C, B, A, right? So that will be the direction of the current flow. Similarly, in the third case, now you can try, you can pause the video and try it. Now when you pull this loop outside, again the flux will decrease. So just like in case 2, when the flux will decrease, so the current will set up itself in such a way that it will not let the flux to decrease, means it will create a magnetic field that supports already existing magnetic field. So current will set up itself in such a way. Use right hand, curl the fingers of your right hand in the direction of the induced current, then the thumb will point away from you, means the new field is in the direction of already existing magnetic field. So the induced current will be in the clockwise sense. So here the induced current will be A, B, C, D, A, right? Now, in order to understand Lenz law, let's solve these problems. In all these problems, we have to find the direction of the induced current in various situations. Now here, this is a bar magnet that is moving towards the coil. When this magnet moves towards the coil, means there is an increase in flux. Now, as per the Lenz law, the increase in flux will not let the magnet to come closer. So how the magnet is denied to come closer? So a south pole has to be established on this face. So this south and this south will repel each other. Now how to set up the direction of current in this coil? For this, look at the movement of the fingers of the right hand. So this is the right hand. So you will wrap your fingers around the coil in such a way that thumb will give the direction of the magnetic field or the dipole moment of the coil. Now the dipole moment of the coil must be towards left. See, the magnet is moving towards the left and the thumb must be towards the left, such that there is a south pole here and the north pole on this side, and inside the magnet the direction of the field must be from right to left. So in order to do that, the direction of the current as per the wrapping of the fingers will be in this direction, means upwards. The current will be in this direction, right? So for the last coil, if I consider this last coil, so here the direction of current will like that and the current will flow like that. Okay, so if we have to write, so the direction of current is from Q R P outside the coil, and inside the coil it is from P to Q. So I will write outside the coil. So the best way to do such kind of questions is to use the wrapping of the fingers, use converse of right and thumb rule, curl your fingers in the direction of the induced current, then thumb will give you the direction of the magnetic dipole moment. So for repulsion, both the dipole moments has to be in the same direction. Only then there will be repulsion. So that south or north will face each other, right? So in this situation, it is clear that the current will be in this direction. Clear? Now, if we look here in situation B, the magnet is moving towards left. So if we look at this coil, so here we have a south pole, and again here it is north, so here we have a south, and here we have north pole, right? So if we have a south pole here and north pole here, means inside the coil the direction of magnetic moment should be like that, south north, direction of magnetic moment is like that, so that the current must be in this direction. So if you wrap the fingers around this coil, so the current must be in this direction. So when the current is in this direction, so the direction of current here will be like that. So this wire is supplying the current in this direction, this current is moving inside, and this starts swirling like that. Okay, so for the left side we will say that the direction of induced current will be like that, PRQ. Now if you look here in the right coil, so here the north pole is moving away from the coil, so here we will get south pole and here we will get north pole. So the direction of magnetic moment for this coil must be in this direction. So in order to maintain the magnetic moment in this direction, right, this means you have to have your thumb of the right hand towards right. So you will wrap your fingers in such a way, you will curl your fingers in such a way. So for that, when you are curling your fingers in this way, in this way, so the direction of current will be like that, downwards. So the current is coming towards y, from y to z, and z to x. So this will be the direction of induced current, right? So in this situation, here we have south, here we have north. The magnetic moment is in this direction. Here we have north, on this we have south. The direction of moment is in this direction. So correspondingly, we have the direction of induced current, right?